Next slide, please. And what we're going to be talking about today is the technologies we have at Fischione Instruments to thin samples for transmission electron microscopy work. And the key is making a sample as thin as possible, usually thinner than a human hair, and finding a way to image at the atomic scale what's happening with the material inside. And the building block for that process is what we call sputtering. Not what happens when your car doesn't start in the winter, but if I may use an analogy, let's take a bowling ball and think about tossing that at a set of bowling pins and trying to knock one or more down. We're kind of doing the same thing, but now we're going to use energetic atoms called ions, and we're going to take ions, toss them at a surface, and controllably remove the ions from the specimen surface. And if I can use the laser pointer here, just to say a few words about the physics of sputtering and some of the terminology that you might hear bandied about the building. Well, what happens is when we have the bowling ball coming in, M1, and the ion going out, M2, there are some equations that describe what happens. And the sputtering yield is one important term, and that is basically how many pins you knock down with one throw of the bowling ball. And on the x-axis, we have an energy scale, which is kind of how hard I've thrown the ball when I tried to hit the pins. And depending on the target material, there's a curve that can form. There's a minimum energy below which nothing happens when I throw the bowling ball. Above that, the harder I throw it, the more pins I knock down. And some materials sputter very quickly. For instance, gold and silver are some well-known materials that you usually don't want around in an ion-bombarded environment, because they will leave that surface very quickly and redeposit all around the chamber. Others, for instance, titanium that we use for parts in the 1050 or tungsten that we've used in the past, those tend to not be ejected and end up, being found in the wrong places in the environment where the sputtering is going on. Next slide, please. How does the sputtering yield truly vary for different materials? It's not exactly easy to understand. If you know the periodic table that you may have seen in chemistry, in general, as I increase the atomic number from, say, carbon at 12 to silver or gold or tungsten at, I believe, is at 74, in general, the sputtering yield goes up. So there's more ions ejected for each incident one, more pins knocked down for each bowling ball. These family of curves are for various energies that we would usually use, 500 eV or 0.5 kV, up to 10. And all I can say is if you look at the periods in the periodic table, the families of elements, there's also an increase. And the thing to just remember is that if you ever have a situation where you want to know what happens, look at curves like this. And again, sometimes what you'll find is some materials that you wouldn't think might be a problem, they can be. For instance, silver, gold. There's some others that you would think, high melting point material, metal, I wouldn't see it redistributed around, but yes, it can occur. Next slide, please. Now, let's talk about commercializing an instrument and using the sputtering process to our advantage. Terminology now changes to what can we do to ion mill material. And where that came from is just, you guys in the back. Are there any guys from the back? Well, in the back we have milling machines, for instance. And milling in a mechanical sense is just having a table move back and forth with tooling and going layer by layer down through a material with a physical machining process. We're kind of going to do the same thing, but now we're going to do it in a different way. We're going to use the energetic ions. We're going to use the bowling balls to remove material layer by layer and optimize the surface. And the process can be defined by taking non-reactive ions. We don't want to have ions that chemically react with the surface, hence we usually use argon, which doesn't chemically react with the ions on the surface. The thinning continues to be by momentum transfer. As far as what the actual rate, the milling rate is, it depends on a lot of things. I'm just going to give you a little laundry list. And you could spend the rest of your life studying it, but you don't want to. But what you need to know, of course, is the relative mass, as we've seen, M1 versus M2, that controls the sputtering process, the atomic number of the specimen, which we've talked about. Sometimes the specimen crystal structure can play a role. Basically, the density of stacking of the atoms or ions in the solid. Milling angle, which is the angle of inclination of an ion source to a material, the specimen surface. Specimen temperature can play a role. And finally, of course, how hard we're throwing the bowling balls, the overall energy of the argon ion beam. Next slide, please. As far as that angle, it's defined here, theta. And when we talk about milling, we think about, again, an ion source energizing a gas, forming the argon ions, which are inert to the surface. And usually we have a beam of some diameter. So within this beam, there's thousands, if not millions, of ions hitting the surface over the course of an hour, and and basically causing sputtering to occur. Next slide, please. As far as that angle, how does that vary with rate? Well, folks have known for quite a long time that as we vary the rate, it doesn't matter what the material or the specimen may be, it goes through a maximum. Therefore, most commercial instruments work in this linear range. So if this is 10 degrees, that's usually all we need to have a controllable situation in a commercial instrument. Above that, it becomes slightly uncontrollable. And why this maximum occurs it depends a lot about the crystal structure of the material. And sometimes there's a law of diminishing returns. If we throw too many bowling balls at a surface per unit time, we can actually get back sputtering. So some of the ions that are coming off the surface are coming, or the bowling pins are coming back towards the bowling ball and keeping the next bowling ball from hitting its mark. So that's how we get that maximum. Next slide, please. If we go too high an angle, above 15 degrees, we can actually etch the surface. So we're not taking material layer by layer. We're ending up with a bunch of hills and valleys on any given material just due to geometry. If we have differences in atomic number, for instance, let's say we have tungsten carbide cobalt, what makes up an end mill back in the shop. Well, what can happen is, let's say the low Z material is the cobalt binder, the high Z material is the tungsten carbide. The surface will end up with lots of nooks and crannies because the cobalt has a different sputtering rate, higher sputtering rate, because it's low atomic number versus tungsten carbide, and these steps persist. If we go to the next slide, the fix is for most of those types of cases, if we just keep below 15 degrees, actually below 10 degrees, and allow the angle to work for us, so that we have to take down the high Z material before we get to the low, we can end up with a very flat sample or specimen as a result. Atomically flat when we're done. Next slide, please. As far as that effective specimen temperature that we noted on an earlier slide, well, what happens under an ion beam? Well, believe it or not, you can have heating due to the interactions of the sputtering process, and folks have measured as much as 100 or 200 degrees centigrade, right where the ion beam is contacting the material. And what happens, it depends on the temperature, but most materials, of course, we don't want to alter them. If the temperature is too high, what can happen is we can create excess point defects, which are basically empty spots where an ion has come out from the material and there's just a hole left. We can have a whole row of those, what's called a line defect. We can have groups, which are sort of a three-dimensional defect known as grain boundaries. And if we have a tungsten carbide and cobalt, now that's probably not a good example, but in some cases, similar materials, we can change how much of each material, component material makes up the host material itself, just from heating. It's like annealing a material. You've changed it. You can move defects around, so even though you haven't added any, you've just like
move the existing ones around, which is not good for the material. And you can have an increase in amorphization. We're going to talk a lot more about that in a second. But what that really means is the orderly stack up of the ions that make up a solid. Basically, we take that three-dimensional. Now we're talking 3 dimensions. We have a row of bowling pins, if you can imagine that, and let's stack another row atop of that, and another row atop of that. Well, we'd like a nice orderly array. That's like a perfect material. But if we would take that stack up and just shake it like crazy, and so our bowling pins are just all mixed up like a bowl full of jelly, that's amorphous, from the Latin without shape. So that's all amorphization is taking the perfect solid and making it less so.
So, Rocco, I have a question. Like when
Yes.
when you are hitting with the iron the surface,
Yes.
are you also ionizing the very few nanometer of surface layer?
Yes, you're breaking bonds. You're breaking bonds. The atoms are bonded,
But
and
are
basically
you,
a neutral species in the material.
But when you are saying the point effects, you are taking out electrons from the from somewhere.
Yes, well, you've broken a bond. So let's say that you have an incident ion, and in some cases what you can have is you can have secondary collisions. So the ion hits the surface, and let's say the sputtering yield is more than 1. Well, one ion may go out, but another ion may go in and knock one of the ions that are in the solid off its spot. It can either come out and there'll be a hole left behind, or it could just be interstitially kept. It can be jammed in like a little empty space that's between the bowling pins, and you have a hole where there's no bowling pin. So there are some secondary collisions that obviously that occur. And just following up on this, in terms of specimen temperature, how do we cure it? Well, our company is a strong believer in cooling the sample, and that's why you'll see a liquid nitrogen container on most of the ion mills that we produce.
And like when you are, the milli angle is too high, are you redepositing some of the materials on the somewhere if the milli angle is too high?
Well, if it's too high, then you have greater penetration. I'll show that in a minute, but you can do simulation. So if you do have a higher angle, there's a volume where the bowl full of jelly is occurring, and as you go to a higher angle, greater penetration and more probability for amorphization or preferential milling.
But what about the redeposition somewhere on the?
Well, sure, redeposition can occur. I guess the idea is that if we're usually, I mean, if we're only working on one surface and we only have one set angle, I wouldn't expect redeposition to occur. If we had, for instance, well, we'll talk about that a little bit more in a minute in terms of some different geometries. Let me just see how we're doing on time here. Oh, we're halfway through. So let's just talk a little bit about the ion energy. We talked about how fast the bowling balls go in and the strength that we throw them. Well, higher energies, what could happen if we go too high? What's known, if we go below about 6 kV, we're in the realm of commercial ion milling instruments. As we get above that, especially 10 kV, actually the thinning rates for some materials, actually most materials will actually start to decline. There's a lot of reasons for that. Part of that is, again, the law of diminishing returns, where we're creating more defects, we're having more back sputtering, and a lot of weird things are going on. But that's the story as why we don't want to go too high in energy. Actually, some additional problems can occur, more defects moving around. Lower energies, the thinning rates are always more predictable, and that's our sweet spot for optimizing sample quality or specimen quality. That's where we want to work, 6 kV and below. Next slide, please. Amorphization. Now, let's say that we've designed, as with all these great engineers I know we do every day, very, very well thought out ion milling devices, and we're not worried anymore about excessive ion energies, excessive temperatures, a lot of the things that we've seen that now we've limited and now done without. Well, there's one problem that remains that is just due to the physics of the sputtering process that we probably can't necessarily eliminate, but we could almost eliminate. We could minimize it greatly. And that's how much residual amorphous damage we have on any material. And that's that bowl full of jelly layer that occurs right at the surface. So no matter what energy we use, no matter what angle we use, no matter what temperature we use, there's always going to be a little bit of something on a sample that's not good, but we hope to minimize it greatly by using proper application of technology. Now, with all the great microscopes out there and with all the techniques, we really don't want to have much of this amorphous layer, and I won't go through this stuff in detail, but essentially if we have the bowl full of jelly layer too thick, we can limit our imaging because we're looking through basically a mask to the real material below. So we're looking through this mask that's filled with defects and trying to study the material below. Same thing if we chemically analyze, we're going to have some problems if we have a strongly defected layer over the material we want to study. And as far as specimen thickness, we want to get the sample as thin as we can. And of course, as we get a sample thinner, if the percentage or the ratio remains the same amount of bad stuff over good stuff, we can get ourselves into a hole as we try to make the sample thinner if we don't control this situation. Next slide, please. As far as the current resolution of a TEM, just to give you an idea, with the corrected microscopes, with the microscopes out there today, they're like 5 million and up, which are very common. We've not gotten to the point where our resolution for imaging is less than 1 angstrom, which is the size of an atom or an ion. We're like half of that now. And that's less than 1/10 of a nanometer, actually less than 0.05 nanometer. So we don't want a layer left on that surface that's actually too much more than this, or we're going to have all kinds of trouble. Next slide, please. Now, let's say we start and we're working on a project or we're working with a material and we want to predict a priori how much amorphization we'll have left. I just thought I'd give you a little laundry list so you guys would have some tools if you want to go forward, because it's probably the most useful thing, I think, for probably especially for our engineers is, well, there's plenty of equations out there that by trial and error, people have done some samples, they've measured some thicknesses of this amorphous layer, and there's some equations that aren't far off. Here's one that's favored by this guy Barna, who's really famous in the whole theory of sputtering and ion milling samples and whatnot. And for a given ion and a given material, this is pretty close in terms of what you could predict to what you would observe in the TEM. So after 0.5 kilovolts argon ion milling, experimentally they found 2 nanometers thick layer, and they had predicted 2.2, so not far off. Next slide, please. That's a 10 degrees angle in terms of incident angle. Another thing you can do is if you go online, you get this famous or infamous free software, depending on your point of view. It's called trim/shrimp. And you can simulate also the sputtering process and predict fairly accurately how much amorphization will be left. And in this software, you could vary the angle from 10 degrees to 90 degrees, choose different ions, not just argon, you can use gallium or whatnot, and different materials, just not silicon, just whatever you want, and figure out what's the bad layer going to be like. And here, they're predicting about 3 nanometers for 1 kilovolt argon on silicon at 10 degrees, which is in the ballpark, not too bad. Next slide, please. But what I would highly recommend is read technical papers, because just to be sure, it's always good to have the experimental data. And just to give you an example, silicon's been well studied, and it's often a material that's often used to calibrate systems, whether they be conventional ion mills, the NanoMill, or the pico mill to come. And you can look at charts like this and figure out for the angle that you're interested in and for the voltage of the ion source, how much amorphization will be left over. And again, you can see that even at 1 kV and roughly 10 degrees, you're still looking at about 10 angstroms, or 1/10 of a nanometer left. So for conventional ion mills, you know, you're pretty good, but of course, remember when we said the size of an atom, it's more like 1 angstrom, or 1/10 of a nanometer, and what the TEM resolution was, less than that. These are some kind of big numbers. And so the push was on to get better at that. in terms of leaving less bad stuff behind. Next slide, please. The same kind of, just to give you one more example, charts can be found for other ions. The FIB, or focused ion beam technique, that is the basis of the new instrument that we have, STIOS. You can take a gallium ion, use much higher energies, up to 30 kilovolts, and use it as a cookie cutter and cut out a small sample that's almost perfect and take it over to the TEM. There's a bunch of other stuff that has to happen, and we'll show some examples. But the idea here is that most commercial focused ion beams, you can get down to about 5 kV or so, and you're still looking at a damage of a couple nanometers or more in terms of the bad layer. Next slide, please. So, we've talked about sputtering. We've talked about ion milling. We've talked about different ions. We've talked about designing instruments. Okay, where are we at Fischione Instruments? Well, we got the best thing going today. We got the NanoMill, and it's going to get it even better in a short time with the Pico mill. And what we want to project to those that are in our user base is that we can follow a new path to create almost a damage-free specimen. There might be a little bit of amorphization left, but it's the best going today. And the idea or the process is use a focused ion beam, cut out a material, polish it at 2 kilovolts with a gallium ion source, so we only have a couple nanometers of junk left. Use an ultra-low energy ion milling system, the NanoMill/Pico, and get that layer to where it's almost gone. Plasma clean it, go to the TM, and get these really great images, and do some really great chemical analysis. Next slide, please. And what were the drivers of the technology? For those that haven't been with us, we've been working with this project actually since about 99 or 2000 it was first envisioned. And even at that time, what we saw was, of course, the decreasing feature of some of the decreasing feature size of some of the stuff that makes up a given sample. For instance, semiconductor samples that have all the little circuits, the devices, the building blocks called transistors, are less than 20 nanometers themselves now. So some of the little doodads that make up a specimen are extremely small, and to image them, we can't have a big layer of junk over top of them when we're done with the ion milling process. Increasing resolution of the TEMs, which we've talked about, and the use of some of this conventional wisdom that wasn't getting the job done, and in that case, the residual damage that remained. Next slide, please. And this is just a timeline showing that after the initial development, patents were issued, and the state of the art that we have right now with the NanoMill, the 1040, is an ultra-low energy ion beam that can operate well below 1 kilovolt. A beam size, as you see here, and the ability to raster it over the specimen, do the milling with these types of milling rates, which are reasonable for the work that we need to do. Next slide, please. And now I'm just going to launch into just some examples to show you how spectacular the results can be. This is just the periodic table that we had mentioned before with the family or periods of elements. And what I've done is darken in some of those to show a lot of the materials that we've done over the years. And I'm going to give you a little laundry list of results. Next slide. And as far as a FIB specimen or sample, if you really aren't familiar with that, there's some various types. In addition, of course, we have the conventional sample. Next slide, please. And what I'm going to show you is after the shot of the NanoMill, and here's the 1040 that is going to be superseded by the Pico. I'm sure everybody's seen it, but that's actually what it looks like. And if you ever want to stop by, of course, we have one in Applications, and I can show you in detail the hardware and the software. But in this box, we have the computer that runs the system, valving, vacuum pump. There's the main chamber with the load lock, so that we can take the sample from the room environment into vacuum. Here's the software up, and we're going to control the ion milling process very precisely. And we do have a liquid nitrogen cooled specimen stage, so we can cool the sample and make sure that it doesn't warm up during the milling process. Next slide, please. Here's the little holder for the sample. This is conventional 3mm TM grid.
but a fib sample would go in basically the same way. And you can go ahead, next slide. And here's the fib sample. Here's our bread and butter. Most of the fib samples that we do are called in situ lift outs. So we have a little 3mm half grid with some little tiny fingers. And the idea is that with a focused ion beam, you can cut out a sample that's 10 microns, let's say by 10 microns by maybe 100 nanometers thick, and you can weld it to the side of this finger. And so that's your samples, teeny tiny. And the idea with the NanoMill is once the sample's brought in the chamber, we can control the angle, the attitude of the sample in terms of its rotation. And as we sputter away material, electrons are also released, as Anjana pointed out. And if we use a secondary electron detector, we can create an image while we're sputtering. And how the NanoMill process usually works, this is the half grid now viewed. That's the little teeny sample. If we draw a box with software, we can tilt the sample one way, mill one side, then tilt it the other way and hit the other side. So we can do top side milling, bottom side milling on the fib sample. And that's the nanomilling process. We tend to work usually in the range of about 200 EV or 0.2 kV to 2000 EV or 2 kV, but we can run this ion source all the way down to 50 EV if we want to and try to minimize the amount of amorphization that's left on the sample. Next slide, please. Here's the old software. I'm sorry, Ben, I don't have the new software stuff, but this is the old software, which works perfectly well as the new software. But here's actually what you interface with if you're standing in front of the machine or the instrument. You only need basically one software page to operate. Up in the left corner here, there's some controls for getting the sample in through the load lock, tilt and rotation of the sample, turn the ion source on, set the EV and the current. Here's some stuff for scanning at various rates and focusing in terms of the image. And here we can control the milling process. Basically, we tilt, rotate, the ion source is on. After we click on some stuff over here, we set the time and we mill. And that's about it. So the training for use of this instrument usually takes less than an hour, and you're off to the races. Next slide, please. That's topside milling at a positive angle. We tilt, we do the bottom side of the sample, and for the in situ work, in situ sample work, usually less than a half an hour, and you're done. You prepared a sample after fib, and now you're ready for TEM. Next slide. Just to show you some other samples that you can process with an NanoMill, this is a conventional sample, like a 3mm disc. Let's say that you've electropolished, like a metal has a hole in it. You can just trim that edge and get a better result filing the TEM. Next slide. This is an H-bar, so it's kind of blacked out here, you can't really see it, but it's a big bar of silicon. We've hogged out material on either side of a small fib sample using the focused ion beam, and now we're going to draw a box and do the same thing we did before with the sample that was on the half grid. We're going to remove material from the top, the bottom, and then we'll go to TEM. Next slide. As far as the full recipes, we have a good knowledge of what parameters to use. Again, the times, they vary, it depends on the initial thickness that we have, but we have data like this, next slide also, for metals, for ceramics, for layers on other ceramics, all this kind of information is available. Next slide. What you see in the TEM as far as amorphization, we have had some stellar results where this is for titanium. So this was a titanium disc that had a hole in it, and then it was nanomilled. Here we have this big, thick, it actually here looks like a layer. But if you could imagine, this is the hole. This is actually a wedge in 3 dimensions. So this junk is where the sample gets thin. The amorphous layer is kind of wrapping over the edge of the material that's around the hole. And if you nanomill that, you can actually take this and remove it and only have what we call lattice fringes, or you can't really see it very well, but rows of atoms evident in the image that go all the way up to the very edge of the hole. So there's no more overlapping bowl full of jelly on that particular sample. So if you go quick enough from the NanoMill to the TEM, such results actually are possible. Let's go to the next slide. Just to give you an idea what the fib damage looks on a metal, like on a metal. Sorry, my laser pointer wasn't working there for a minute. All these little dots here are the fib damage. they're obscuring what we're trying to look at underneath, which in this particular metal, this titanium alloy, there was actually line defects, which are rows of holes, if you will, and they were put in by a mechanical deformation process. So that's really real defects, and that's what we want to study. Well, after the nanomilling process, here's after fib. Now after nanomilling, you can see the little dots are gone, and we can see these little squiggly lines, which are actually like little soldiers. They're the defects that were produced by mechanical deformation that we want to study. So no problem with the nanomill. Next slide, please. Silicon, what can you expect? After the focused ion beam process, often we see bigger splotches. We don't see like the little splotches, we see a little larger splotches, but they're also due to the focused ion beam process. Basically, that's coming from a bowl full of jelly that's distorting the image. This little diagram here is called a fast Fourier transform, and you don't even have to remember that after you leave. But the idea is that with this type of diagram that we can project into TM, the more spots that you have and the farther out to a radius they exist, the better quality material, the less dimorphization occurs after a milling process. So we can start out with something like this before the nanomilling process, and after we have a lot less of those defects in the image and a lot clearer FFT over here, and sometimes a few more spots out to a larger radius from the center of that little diagram. Next slide. If we would go to a better TM with that same sample, we could start to clearly see the atoms or ions in the silicon that make up the structure. And you can see you've got a lot more spots here, right? And out to a greater radius. If you go to the next slide, if you take a new piece of silicon, like these guys at Berkeley, and get it extremely thin and almost free of amorphization, this sample is actually 7 nanometers thick in this particular area. You have these really great images. You can really see all the little ions. And these are called doublets. In silicon, if you look at certain planes of silicon, there's two little spots that are actually two ions. I don't know if you can see them, and they're very, very close together. And that's kind of like the holy grail for silicon imaging, and they're clearly obvious here. And you can see how many spots you have in this FFT, how much information out to such a great radius, which means this is a stellar sample of silicon. Next slide. We're going to try to speed up and finish up. We're a little bit over time. Just to show you some more examples, let's say we take silicon and jam in another ion, germanium. This is 2 layers of silicon that have been modified by adding germanium. And after the nanomilling process, you can clearly see this change in contrast. In this type of image, which is called a scanning transmission electron microscope image, the ions that are higher atomic number are brighter than the ones that are lower. So germanium is like 32 and silicon's, I don't know, 14. So you can clearly see where the germanium is. You can't really pick out individual ions, but it's definitely brighter here than over here. Next slide. If we take now, let's take a layer of something, put it on silicon. Here we have layers of silicon oxide on silicon. This is the fib sample here. So that's a little sample there. You can see the marker is 1 micron, so that's about 10. I'm going to quit using this because it's unreliable. But it's about 10 microns by about 4. You rotate in the nanomill. We cut off this corner. Here's your cross section. This actually is a little platinum cap that was put down in the fib to protect the material during fibbing. These are the layers. That's the silicon. Next slide. And here's what we would call the cross section. And that's a bread and butter for the nanomill to get really good cross sections. Those are the conditions that were used for nanomilling. Next slide. This was nice. This was published data. I did this sample for a group in Europe years ago. And what they found is they looked at these layers in detail. Next slide. And what they found is little small areas of silicon within the silicon layer. So this is a silicon substrate. Then there's silicon oxide, more silicon, silicon oxide, silicon. And they found a different lattice spacing for those ions in this little doodad that's different in the layer itself. And that was something they'd never seen before. And they said that opened up like a whole new direction for solar materials, which is what this material was a test bed for. And here's the FFT with a lot of information showing that indeed this is some new type of silicon that they hadn't seen before in terms of its stacking of the ions. Next slide. Great thing about the nanomill is we could get areas that are not just thin but uniformly thin. They wanted to study the chemistry, silicon and oxygen. This is a technique called energy filter TEM, so you only do some of the electrons that come out of the solid to create images and maps. And what they were able to find is on the nanometer scale a very reproducible variation in silicon and oxygen across those layers. So it's kind of difficult to do, and you need like a really, really uniformly thin sample to do it. Next slide. Let's just take a few quick more examples. Let's take 3 ions and put them in one solid. So this is a barium titanate. So there's actually barium, titanium, and oxygen making up this material. This is a strontium titanate, strontium, titanium, and oxygen. It's often difficult to pick out the individual ions. The holy grail there is to get all 3 visible. Now you can definitely see 2 where you're sitting from, the bright ones and the dark ones, right? Well, often if you zoom in, you can even see a 3rd one, which you can't see in this image. But all that's done by proper focused ion beam technique and nanomilling on these types of materials. Next slide. If we glue 2 of those together with an interface in between, let's say we grow one on another, after the focused ion beam, it may not be clear where the interface is between the 2. After a little nanomilling and cleanup, you can clearly see, I think, where the one material ends and the other begins. And that's indicated in these curves. These are just intensity curves, brightness, darkness, essentially. Here you can't see where the interface is. Here you can see this transition where the interface is in that image. Next slide. Okay, where are we on this whole amorphous deal? Because I just thought I'd throw this in. Again, truth in advertising is that we're the best thing going today. Now, on some materials, for instance, this is a multi-layer, not silicon oxide, but moly and silicon on silicon. And we can start with a fairly thick amorphous layer after the focused ion beam, and we can reduce it. And in this case, the customer was happy as a clam. But of course, for many materials, it may be hard to get below 1 nanometer or so. It just depends on the particular material and the particular sample. So next slide. This is just to show an H-bar before and after, just to show a different type of fib sample. It's often difficult to do. We were talking about redeposition, these particular samples, because of the geometry. You may recall you had a big bar and you hogged out stuff on either side. You had this thin layer sticking out towards you. Well, it's kind of hard to sneak the ion beam in there, the NanoMill, without hitting the side walls around the hogged out area and putting stuff back onto the sample by back sputtering. Well, we're able after fib to basically clean up those samples, and if we're careful in the way we do it and keep the box small, there's a good result to be had. Next slide. And, this is another totally different type of fib sample. They're becoming very popular. They're needle type samples. If you can imagine, the sample itself is probably a few microns tall by maybe 100 nanometers in diameter. And there's a lot of advantages for those type of materials in those type of geometries. You can do mechanical testing on them. You can use our 2050 tomography holder, spin the sample into TEM and do tomography and some other things. And we can nanomill those samples also. Here's the needle, gallium nitride. And after we do some nanomilling, without going into this whole caption, I just will leave you with, look at those ions, aren't they beautiful? Just going right out to the vacuum in the TEM without any amorphous layer. So there are definitely ways that we can achieve this, and there's an example right there. So next slide, I think, is just my summary, and I think we've talked about the evolution of the technology pretty well, the removal of ion damage, we talked about amorphization, and I would like to thank everybody for their attention, and I can answer a question or two if there is one. Thank you very much.
Will Pico replace NanoMill?
I think that's a question probably for sales and marketing. I would, or maybe Mike could comment. Mike's shaking his head.
No, it won't replace it. It will. They're for 2 different markets, price points. Whether you need the ability to do endpoint detection. So no, it won't replace it.
So the samples, what could be achieved on Pico and on NanoMill, they will be different a little bit for the slice or size thicknesses, right?
More for the image
Yeah, it's more for the ability to image it while it's in the mill itself. The ion source, that's going to be more of a question for sales and marketing, whether the ion source in both systems will be the same. We've made some improvements to the ion source, and we can image better with the ion source itself, plus then we have the SEM column. But that would be a sales and marketing question, whether we put a better imaging ion source in the NanoMill. But for right now, they'll still both be able to prepare the specimen the same, just a matter of how well you can see the specimen with the ion source.
Well, and of course, the other thing was we do have a smaller ion beam size with the Pico. There might be certain advantages going forward.
I know.
And-
Holder is also.
And that's what I was going to say, the holder,
Holder is one of the advantages.
we have a TM holder with the Pico, so that the transfer to the TM could be really rapid.
Yeah.
If you could just take it out, you go right to the TM, and that's one of the, of course, critical issues. We've actually made a vacuum transfer device or inert gas transfer device for the 1040, so that you could kind of take the existing holder out to the load lock and just attach, and then go to a dry box, and then or a box under inert gas, or and transfer to TM holder. But a lot of folks would rather just take the sample on a TM holder out of the Pico and then just put it right into the TM, which we'll be able to do.
And also you have the stem detector, which you can see the sample, how much thin it is,
Yes,
which NanoMill doesn't have.
that's true. Yeah, the idea with the Pico is we have a way to detect as the ions, so that a stem detector basically is, as in a TM, you can have a detector underneath the sample position. So you can, and in the Pico we have not just, in the NanoMill we only have an ion source and an ion column. And then we have a secondary electron detector that creates an image. And it's a pretty good image, but it's only up to a few thousand times magnification. With the Pico, we have a dedicated ion source, which we can't image with, but then we have a dedicated higher resolution electron column with an electron source. And so we can have the electrons incident on the sample, have a stem detector underneath, and you can calibrate so that you know how thin the sample is. For the NanoMill, true, unless you take the sample out of the NanoMill, go to TM and make a measurement, you don't actually know where you are in the process. So hence, it gets difficult sometimes for us to quote times. We know generally at the time, but as I mentioned during the talk, it really depends on how thick the sample you have, and you have to kind of predict where you want to end up based on experience. Any other questions, concerns? Yes, sir.
What is the energy of the electron source would be in the Pico mill?
Does it go up to 30? I don't know, but it might.
15 kV maximum, but we won't run probably that high. Between 10 and 13 for the moment.
So would there be like a limit on how thick of a sample you can put in to begin with to be able to image something with the stem detector?
Well, that's the thing. If you get a better image with a higher energy, but then you lose the ability to see the thin samples because it goes right through it. So you have to kind of decide where, how good of an image you need versus how close you want to be able to monitor the thickness. So it'll be at 15 kV. You probably can't do a whole lot with it because you'll go right through it, even at 13 or 12 kV. 7 is probably the target. So 10 is probably a good compromise for resolution and also being able to monitor the thickness.
Just thinking, doing a calculation in my head, 30 kV, you historically could get through about 500 nanometers. That's what I recall for silicon. Mm-hmm. So even 15 kV, you could blow through like 250 nanometers, I think, which is way thicker than most of our, even our specimens that we start with. So yeah, that's a little bit too much. Any other additional questions? Mina?
I have a question, but it's not really related to the NanoMill. It's actually related to sputtering in your first.
Oh, I thought you were going to say opera or something, like something I really knew nothing about. Go ahead.
So can we go back to the first slide of the presentation?
How far back?
Yeah, this one. So my question is, so this is related to sputtering.
Mm-hmm.
Is it related to sputtering by a focused ion beam or a rolled ion beam?
Oh,
Does it
yes.
matter?
Even electrons, as I think we talked about, what people don't realize, even electrons, they almost have no mass. But you can drill a hole through a sample, as I had Anja asked her to do. Remember you drilled a hole through silicon for us? So yeah, it's basically just, this is of course, is kind of the Newtonian model. That's what I wasn't going to point out, but if you think about this, it's okay actually to use bowling balls as an analogy, because this is assuming like basic physics. And that's why I always point out, we got to remember, and that's why the amorphous layer really forms like it does, is quantum mechanics means you can't, kind of always determine where something is and what it's doing at the same time. So on a solid, it's not really a billiard ball coming in or a bowling ball coming in and either another billiard ball or a pin going out. It's like statistical. The ion may hit here, and the ion that's sputtered could come from here, 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 here. There's like, most we can say is there's an interaction volume that occurs. So this applies to anything that follows basic Newtonian mechanics and physics. And of course, when you start talking quantum mechanical, then it's much more descriptive and more exact. So, and of course, some things like electrons that have almost no weight, I'm sure that the interaction volume will be much different than something that does. Did I scare anybody with that response? Hopefully not. It's just physics. We got a lot of physicists here. If you have another question, ask Wes or Ira. I'm physics of metals. That was my PhD, so I shouldn't be spouting off about Newtonian versus quantum on anything. So, but any other questions, concerns? You can stop by Applications, of course, anytime. If you have any questions and you'd like to discuss anything, I'm available. Anja is available. Mina's available. Stop by, and we can also show you the microscopes, the focused ion beam, NanoMill. We can Tom Sawyer you, make some samples for us, maybe. You never know. So, okay, thanks very much.
Thank you.